Welcome to another video in the series about the C7000 compiler. While most other videos focus on explaining a single feature of the compiler, this one is different. It shows how to combine several features together. My name is George Mock, and I'm your guide. Earlier videos in the series tend to focus on a single feature. This video asks the question, what does it look like to combine all these features together? And there's one example in this video that combines together these features, including the streaming engine, streaming address generator, scalable vectors, vector predication, the restrict keyword, and software pipelining. What does that look like when it's all happening at once? The README for version 4.1.0.LTS has an example based on memcopy. It is named memcopy scalable strm. The interface is similar to the standard memcopy, but it is not a match. The video will introduce this example, then explain it a few lines at a time, and then finally review it all at once. Welcome to the example for this video. It is a function template named memcopy scalable strm. So one of the inputs is a type. That type is S. S stands for scalar. It's a basic data type such as short or float. What happens is some number of S, and that number's len, is copied from in to out. Another important type is V. V is a vector of S, and it's the perfect size for the CPU that you're building for. So the copy from in to out happens one vector's worth at a time. Count is how many times the loop's going to run. We compute that here. An SE is used to read from in, and an SA is used to write to out. And these lines configure the SE and the SA. These lines open the SE and the SA, get them ready for work. Here is the key loop that does the copy, followed by closing the SE and the SA. Next, the video reviews the code a few lines at a time, and these are the first two lines. The first line includes the header file C7x scalable.h, and that header file defines scalable types and utilities. And here are two that appear in the example. The using directive means you don't have to actually write C7x : as it appears right here. It's not required to appear in front of the types and utilities from C7x scalable.h. This is different than how it is done in many of the previous examples, where it always wrote them, fully spelled out the namespace that, some utility or type comes from. So now you get to see it both ways, and you can decide which coding standard works best for your team and then abide by that coding standard. The next two lines are the beginning of a function template. If you're not familiar with C++ templates, I don't think you're going to learn that concept from this video, and it'll probably be pretty confusing to you. All the rest of the video really presumes you know C++ templates and function templates in particular. So if that's you, I recommend you stop watching the video now and go master that topic and then come back to it. Okay, so the type name, S is a type name, and it must be a scalar type, int, short, float. That type is not usually explicitly specified, although there is syntax for doing that. It's usually deduced when the function template is instantiated. When you call it, it looks at what is what is in pointing to, and that's what S becomes. In is pointing to some integers, some type int somethings. Well, then S is an int, and so on. The restrict keyword, you notice that it appears between the asterisk and the name of the pointer variable. That is described in the video, the restrict keyword. The final parameter, len, is different from the one used by the standard runtime support library function memcopy. In the case of memcopy, len is the number of characters to copy. In the case of our function template here, memcopy scalable stream, len is the number of s to copy. So if s is ints or doubles or whatever s may be, this is how many of those are going to get copied, and that is not the same thing as the number of characters that get copied. The next line to discuss defines a scalable vector type. The name of the type is v. V stands for vector. Since it's a scalable vector type of s, each element is an s, the length of it is it's the ideal number of elements for the specific C7000 CPU. So to put it in more specific terms, if your CPU has a 512-bit vector and you've got 32-bit wide ints, well then if s is of type int, then you'll have 16 s within 1v. The copy from in to out happens 1v at a time. The next two lines to discuss compute the count of vector loads and stores. So len is a function parameter. An element count of returns the number of scalars in the vector v, and we use it in this type traits way to get that value. So len divided by that value is going to give you the initial count, and then count is incremented in the case where the number of s and v is not an even multiple of length. Okay, so if that's the case, then count is incremented by 1. And you've seen similar code to this in both there was an example similar to this at the very end of the video about the streaming address generator and the very end of the video about the streaming engine. They both did a very similar thing with this computation here, and you would increment it by 1 if length was not an even multiple of the number of operations you were doing in the vector. And the reason will be similar, and we'll see that when we start to talk about the main loop code. The next two lines to consider are about configuring the SE and SA parameters. These lines call the functions that create a structure with all default values for the configuration. In template is for the in parameter, and out template is for the out parameter. We're using SE for in because SE is a read-only feature. SA can be used for read or write, and in this particular example, you're going to see it will be used for write. The next few lines continue the configuration of the SE and SA parameters. This is for the in template for the SE, that's the out template for the SA. All of these settings have been discussed before in the videos about SE or SA, so there's really nothing terribly new to discuss here, although I will point out that the SE has an additional field to change from the default to something else, and this is the ELE type, element type field, the one that says how many bits are in one element in the vector v. Now that the SE and SA parameters are set, it is time to open them. In this case, SE0 and SA0 are the ones that are used. When you call them, they both use the parameter structure that has been configured. The SE also requires the base address, but the SA, that happens later. Next is running the loop that performs the copy. The variable CNT count is the number of loads and stores that will be performed. It's also the number of times the loop will run. The first three statements are creating variables. This is a vector, a predicate, a pointer to a vector, and then assignments are performed to each variable, in the same statement. These function calls here have been introduced before in earlier videos, but I'll review them again here. This first one is for the streaming engine, and the next two are for the streaming address generator, and all of them for 0, so SE0, SA0, SA0. The get ADV, we read the holding register for the SE and advance it to the next one. So it's reasonable to think of this variable temp as, standing in place for the holding register of SE0. The second one, we get the predicate at the current SA offset, assign that to the variable pred. And the third one, we take the current SA offset, add the base address out to it, and assign that to the variable ADDR. Now in previous examples, there would be an asterisk right here, which would mean load the contents at that address. That's not happening in this particular statement. We're copying the address into this variable. vStore pred is where the holding register and temp gets stored to the vector at this address under control of this predicate. And that will be explained in more detail in the next slide. But before I do that, I want to point out that I've built this code for a few different instances of S. S is a unsigned char or a int, and in every case I've tried, I get an II of 1 for this loop. So for a loop that's doing a vector load and a vector store, and there's a lot going on, getting it all into a II of 1 is very good result. This is really what we want. This is really why we're using C7000, to be able to do this much work in a single cycle. This is the first time the video series is using vStore pred, so I want to describe it carefully. Temp is a vector, ADDR is the address of a vector, pred is a predicate. What happens is all the elements of temp are copied to the vector at this address under control of this predicate. Expressed as pseudocode, it looks like this. This loop is walking through each element of the vectors. If the corresponding predicate is not 0, then we copy that element from temp into the element at this address. This looks like a lot, and it is, but the C7000 does this in a single instruction. It is an example of how powerful the vector processing capability of the C7000 is. After the main loop is over, all the memory copying is done, you close the SE and the SA. And this is the end of the function template. Now that the line-by-line discussion is complete, it is a good time to review the entire function template. So there's the name of it. It starts here. This type S is deduced when you call it. These are the parameters. This is where you're going to be reading from. There's where you're going to be writing to. This is how many copies of S are loaded and stored. This type V is a vector of S elements. That's the perfect size for the particular C7000 CPU you built for. This code computes the number of loads and stores that will be needed to copy the buffer. This code configures the SE and SA parameters. These lines open SE0 and SA0. Remember, SE0 is used to read because SE is read-only. The SA is used to write. Here's the loop, the key central loop that performs the load and store. This statement here, loads an entire vector from in. And then this statement here writes an entire vector to the address ADDR under control of this predicate. And remember that the software pipeline loop generated for this code has an II of 1, which means an entire vector is being loaded and stored per CPU cycle. And then the function template ends with closing the SE and the SA. I want to close this video with two references. The first one is to this web address. It's a little bit long, a little bit hard to type in, so I recommend you search the internet for C7000 compiler. I've tried that search with a few different search engines, and I always get this web address as the first result. However you get there, you're at the home page for the C7000 compiler. Here's where you can download it, access the manual, and more details like that. The second reference is to e2e.ti.com. This is for customer questions on any TI product, including the C7000 compiler. If it is a compiler-related question, it will be answered by me. Thank you for watching this video in the series about the C7000 compiler.